Okay, just a traditional check whether everything is fine. Can you see what I'm writing? Can you hear me? I can't hear you, but I said that I'm just hearing some noise, but I think that everything is fine.
I can hear you.
Okay, yeah. Let's continue. So next time, and I think for 1 month I will be available online, offline. Today I'm only online, but next week I will be. I don't know the room number yet, but I will be in person here. Okay, so let's continue, and let's start with autoregressive type processes, AR processes. There is a big problem with AR processes, autoregressive. So that's autoregression, AR. And the big problem is that there are many different formal definitions of autoregression. And that's a big problem. So if you, for example, will ask a question about MA process, anyone, if you just ask ChatGPT for some theorems about moving average, it will give you good results. But if you ask for some theorems about autoregression, then ChatGPT will tell you something that is partially true, partially false, because there are many different sources. So many. That's the main warning. So that's it's a trap. It's a big trap. There are many different definitions of autoregression, of autoregressive process. It's a trap. So that's a big warning. Be careful. So I will discuss all, let's say, 3 approaches to define AR process. And we will discuss how to formulate correct theorems in these different approaches. Okay, so let's start with a simple example. Let's start with an equation. So first I will have equation. I will have equation yt is equal to, let's say, 0.5 yt minus 1 plus ut. I will say that ut is a white noise. And we will discuss all the subtleties of this equation. So first point, what I have written is an equation, is not a process yet. So first idea, so warning 1, equation is not a process. Because this equation, if I try to solve this equation for yt, so I'm trying to solve it for yt. So I'm searching for yt. This equation has infinitely many solutions. So the first problem, equation is not a process. Second warning, this equation has infinitely many solutions. Equation has infinitely many solutions. To prove the second claim, it's just sufficient to show some of them. Let me show that there are infinitely many solutions to this equation. You can choose any y0 or y1. Any initial condition will be okay. So let's say, for example, let's say y0 is 42. Yeah, let's say y0 is 42, and then you can get y1. Or how to get y1? You should take 0.5 times 42 plus u1, so it's 25 plus u1. You can calculate y2, that will be 0.5 times 21 plus u1 plus u2, and you can continue, and you can calculate all values of y. Yeah? So you can continue, you can calculate y3, you can calculate y4. Even more, you can use this equation to calculate previous values of y. So using just one initial condition, you can find all future values of y, and you can find all past values of y. How to find, for example, y minus 1. Y0 is 0.5 times y minus 1 plus u0, and hence if this value is 42, then I can find y minus 1. So it will be 42 minus u0 multiplied by 2. By the same logic, I can calculate y minus 2. How to get y minus 2? I can say that y minus 1 should be equal to 0.5 times y minus 2 plus u minus 1, and hence y minus 2 is twice y minus 1 minus u minus 1, and we can plug in y minus 1, and we can get twice times 84 minus 2 u0 minus u minus 1. And by the same logic, we can calculate y minus 3, y minus 4, and so on. So this example shows us the main idea. Equation has infinitely many solutions. I have shown only one solution, but you see that my choice of y0 was I've taken 42 out of the blue sky. So I can provide you many other solutions. I can start with y0 equal to 0 and calculate y1, y2, y3, y4, and so on. And I can go back in the past, calculate y minus 1, y minus 2, y minus 3, and so on. I can even make y0 random. So I can take y0, let's say u1 divided by u0, plus cosine of y7 of u7, and using the same formula, I can get y1, y2, y3, y4, and so on, and I can go back in the past and calculate y minus 1, y minus 2, y minus 3, and so on. So that's the first idea. When we have written this equation, there are infinitely many solutions to this equation. We consider this equation as an equation for y. We consider u as a process with pre-specified characteristics, and we solve this equation for y. So we're searching for y1, y2, y0, y minus 1. So that's the first, the second warning. Equation has infinitely many solutions, and hence we have warning 1. Which of these solutions is is named autoregressive process? And there are different viewpoints. So if you search the internet, so there are there are three viewpoints. The first one, any of these, so there are three viewpoints, three approaches to define. So in one book, you will encounter one approach. In other book, you will encounter other approach. And hence, if you ask ChatGPT, ChatGPT has learned on many books, on many sources. So some statements, it may pick up one definition from one book and one theorem from the other book. So be careful. So if you ask a question for, about moving average process, you will get a very good response, very accurate statement of the theorem. But if you ask the same about autoregressive process, probably you will receive a mix of definitions, a mix of theorems. And that's not only a problem of ChatGPT. Many humans, for example, if a newborn lecturer or class teacher is preparing for lecture, for class, so she or he may pick up one definition from one book, other definition from the other book, other theorem from the third book, and will receive a not very, something that is plainly wrong if we speak rigorously. And I have encountered many examples of this situation in many courses, even at good universities. So that's the problem. Okay, so there are three viewpoints. So we may consider, we can call any, so that's the first approach. We can say any solution, we can call any solution of yt equal to c plus, let's say, alpha 1 yt minus 1 plus ut, where ut is a white noise. Any solution yt of this equation, autoregressive process of order 1. So that's the first approach. If you work with this approach, then this solution is autoregressive process of order 1. This solution generated by y0 equal to 0, and the solution generated by y0 equal to u1 divided by u0 plus cosine of u7 is also a autoregressive process of order 1. Okay, that's the first possibility. We can call any solution. The second approach, we can call any stationary solution. So, but better some. So let's better say that not we can, but some authors. Yeah. So let's say some authors. Some authors call any stationary solution of this equation, by autoregressive process of order 1. And there is a third group of authors. So in some books, some authors call any solution of MA infinity form with respect to UT AR1 process. The equation is the same. Any solution of, let's say, star. I'll write it star. That's equation star. Yeah. So there are three approaches, three viewpoints, and in different books you will encounter different definitions, and all of them are correct. But if you just with a self-contained book, that's not a problem. But if you Google from one source, from another source, different pieces of different pieces may not match well. Okay, so be careful. Let's consider a particular equation and let's check. Yeah.
I just have a question. This which is what does mean this the third viewpoint? Any solution of equation of main infinity.
Infinity form with respect to t. Yeah. We will. Yeah. Let's provide some examples. Okay. Let's. I will consider some.
I'm sorry for interrupting. I just was.
That's what I. So it was my plan to consider some examples. So okay, let's provide this process. Let's start with an equation. Yt is equal to 0.5 for yt minus 1 plus ut. Ut is a white noise. White noise. And let's provide some solutions and let's write them. Ut is a white noise. So let's recap that white noise means that expected value of ut is 0, variance of ut is constant, and the covariance of different random disturbances is 0 for t not equal to s. That's the definition of white noise. Expected value is 0, variance is constant, and covariance of different UTUF with different indices is 0. Okay, so let's provide. So I will consider, let's say, two solutions. So we know that it has. So this equation, we already know that this equation has infinitely many solutions. Yeah, we already know that this many solutions because basically you can pick any y0 you like. Y0 equal to 10, that's okay, you will obtain a solution. You can pick y0 equal to u0, you will obtain a solution. And so I will consider two solutions. So okay, let's consider two solutions. Solution number one, y0 is equal to 0. Okay, hence y1 is equal to 0.5 times 0 plus u1. It will be u1. Y2 is equal to 0.5 times y1 plus u2. It will be 0.5 times u1 plus u2. Y3 will be 0.5 multiplied by this value, 0.5 u1 plus u2 plus u3. So I will get 0.5 squared u1 plus 0.5 u2 plus u3, and so on. For example, if I start with 0, then, for example, y10 will be equal, the sequence here is very simple. The most recent u has weight 1, and when you go deeper into the past, you will have 0.5, 0.5 squared, 0.5 cube, and so on. So we'll have 0.5 times u9 plus 0.5 squared times u8 plus plus u1 will be with coefficient 0.5 superscript. It will be 9, I hope. Yeah. To go down from the stage 10 to stage 1, I need to go down by 9 stages. Okay, so that's solution number 1. And obviously this solution is non-stationary. Yeah, let's check whether this solution is stationary or not. Expected value of y0 is expected value of 0 is 0. Expected value of y1 is expected value of u1 is 0. But if I will calculate variance of y0 is variance of 0 is 0. And variance of y1 is variance of u1 is sigma squared u.
It seems like it's stationary because it's very looks like a R solution.
No, that's not stationary. No, that's not stationary. You see the variance. The first observation is 0, is non-random. So that's non-random. In my question, my process starts for sure at 0. Yeah.
I see then, yeah.
Yeah. But if I consider another solution, let's consider solution. So solution number one is non-stationary. So now let's consider solution number 2. I consider the same equation. Yeah, I consider the same equation, but I consider another y0. Okay, let's consider solution number 2. Let's consider y0, that is u0 plus 0.5 u minus 1 plus 0.5 square root u minus 2 plus 0.5 cube u minus 3 plus up to infinity. So there is a subtle question whether this infinite sum exists. Probably there are some convergence issues, but you have a theorem. Piotr has given you the theorem that this infinite sum converges. So there are no problems to write. So this is a correctly defined random variable. There are no problems. So it exists, because some infinite sums, they do not exist. Yeah. For example, if you try to add 1 plus 1 plus 1 plus 1 plus 1 and so on, you will not get a number. You will get something like infinity, but infinity is not a number. And in this way, in this infinite sum, everything is fine, because coefficients decrease to 0 rapidly, and hence this sum is well-defined sum. This is a well-defined random variable. Okay, let's calculate y1. y1 will be 0.5 times this infinite sum and if you open the brackets, you will see that this infinite sum has exactly the same structure. Just we see the shift in indices of white noise u. Yeah, you see that u1 will be with coefficient 1, 0.5 will be multiplied by u0, 0.5 squared will be multiplied by u minus 1, plus 0.5 cube will be multiplied by minus 2, and so on. Yeah, it will have exactly the same structure, but with indices shifted by 1. Yeah, the expression for y0 starts with u0, and the expression for y1 starts with u1. If I will calculate y2, the structure of the sum will be preserved. Yeah, if I multiply 0.5 times y1 plus u2, I will get 0.5 multiplied by this sum plus u2, and you will see that I will have u2 plus 0.5 times u1 plus 0.5 squared times u0 plus 0.5 cube times u minus 1, and so on. And hence we see that the structure of the sum will be exactly the same, but with shifted indices. Yeah. Hence, if I calculate expected value of y1, it will obviously be equal to expected value of y2, because the coefficients are the same. yeah, it will be equal to expected value of y3, it will be 0. Yeah, the variance of y1 will be the variance of y2, it will be the variance of y3. It can be calculated as sigma squared plus, so how to calculate variance? The variance of the first term is sigma squared. The variance of the second term is 0.5 squared sigma squared u plus the variance of the third term 0.5 to 4 times sigma squared u plus bam. And I see that this expression is constant. Yeah, it doesn't change. It's not important whether I consider y1, y2, y3. That's the same value. Okay, let's calculate covariance, and let's see that covariance. Now we have a stationary solution. Yeah. So if I, for example, calculate covariance of y1 and y2, and if I calculate covariance of, let's say, y10 and y11, we will get the same number. Yeah, they will be equal. Why they will be equal? How can I calculate the covariance of y1 and y2? If I calculate y1 and y2, in y1 I will have u1 plus 0.5 u0 plus 0.5 squared u minus 1, u2 will be, y2 will be u2 plus 0.5 u1 plus 0.5 squared u minus, sorry, u0 plus 0.5 cube u minus 1, and so on. And I see that to calculate the covariance, I need to find matching indices, and hence the covariance will be 0.5 times sigma squared u, then plus 0.5 cube times sigma squared u, plus 0.5 power 5 sigma squared u, and so on. So that is covariance of u1 with 0.5 u1. That is covariance of 0.5 u0, 0.5 squared u0. That is covariance of 0.5 squared u minus 1, 0.5 cube u minus 1, and so on. And if I will calculate the covariance of y10 and y11, the result will be the same, because indices will be shifted when I replace y1 by y10, and the indices will be shifted by the same amount if I replace y2 by y11. And so the covariances, these covariances are the same. And for this particular solution, for this solution number 2, we will have a covariance of yt and covariance yt minus 1 will be all equal to some number gamma 1. Covariance between yt and yt minus 2 will all be equal to gamma 2, and so on. Covariance yt minus k will all be equal to some value gamma k. And hence, we see the difference between these two definitions. So in a moment, we will discuss the difference between definition 2 and definition 3, but for the moment, we shall be able to see the difference between these two definitions. And in some books, some authors, they say, oh, this solution we call, so in some books, the authors say that, oh, this solution is called autoregressive process of order 1. In some books, the authors say, no, solution 1 is not autoregressive process. Only solution 2 is autoregressive process, because solution number 2 is stationary.
Why are there so many variations?
Why mathematicians have not agreed to one definition? The answer is simple, because that's too popular. So many human beings would like to predict the future. And so there are many schools. Yes, from the student viewpoint, that's pity that, which definition should I use? How I can say theorem on the exam? Don't worry. On the exam, I try to remove this confusion from all the exams. So I will not ask you the question, this is AR1 process or not. I will ask you a more precise question, whether it's stationary, whether this process solves that equation. So I try to block this confusion. So don't be afraid. I will not ask you to guess, this author, which definition he uses. Just my goal is to give you a warning that there are, for moving average process, no problem. All definitions in all the books are the same. But for autoregressive process, be careful. If an author states a theorem, then you should pay attention which definition is used. And there are, I think, 4 types of authors. One type of authors, they use the first definition. The second type, they use the second definition. The third type, they use the third definition. And there is a 4th type of authors who do not understand the difference between these definitions. And in the same book, you may encounter, if even there are good books where authors may give you good advices about how to predict time series, but they do not understand that there is a difference between these 3 concepts. So I have encountered this problem. So that's why I'm paying your attention to this. Okay, so I think we have discussed with these 2 solutions. According to the first definition of autoregressive process, the first solution is autoregressive process. The second is autoregressive process for the 1. But according to the second definition, we see that solution 1 is non-stationary. So according to the second definition, it does not deserve the name of AR1 process, and only the second process deserves the name of AR1 process. Okay, I hope that the difference between the first and the second approach to the rigorous definition is clear. Yeah, we can continue, because the difference between the second and the third is more subtle, and I'd like to be sure that you understand the difference between the first and the second. So the key point here that we require stationarity.
Yeah, we understand. Like from the second type of solution, let's say, is suitable for the first one, right? But it doesn't work the other way around.
Yeah. Both solutions are autoregressive process with respect to the first definition, but only the second one satisfies the second. Okay.
I think what I tried to ask is more like, why do we need then autoregression process? It seems like for every solution we have different goal with what we want.
Yes.
So it's just like a slang name in math. Let's say some shortcut.
Yes, I agree. But when we are studying and we are making some rigorous studies, then we should be clear, crystal clear about assumptions, whether we impose stationarity assumption, whether we do not impose the stationarity assumption. So when you read books or lecture notes, so you should ask yourself or the author whether he includes the requirement of stationarity in the definition. Okay, let's move on to the subtle definition between point 2 and point 3. So that's more interesting. Okay, let's consider another equation. Let's consider equation yt is equal to twice yt minus 1 plus ut. Okay, so let's consider this equation. And let's start with, let's say, okay. So let's consider this equation. Obviously, I can re-express yt minus 1 from this equation. So let's find yt minus 1. But that's obvious. Yt minus 1 is 0.5 yt minus 0.5 ut. Yeah, that's obvious. Yeah. Okay. So yt minus 1. Let's just rename. This. I will rename this by W. Okay. So let's wait. I will rename this. Yeah, I will rename this by WT. Yeah, I will rename this by WT. Okay. So I have an equation of this type. Yt minus 1 is 0.5 yt plus WT, or maybe let's rename it by WT minus 1. So let's just rename it. Okay. But we know that this equation has a stationary solution. We have just provided the stationary solution of this equation 10 minutes ago. Yeah, 10 minutes ago, or maybe 15, we have discussed that these, if I take y0 of this form, or if I take yt of the form ut plus 0.5 ut minus 1 plus 0.5 squared ut minus 2 plus this is the stationary solution. We have proven it, that yt equal to ut plus 0.5 ut minus 1. This is a stationary solution to this equation. And the new equation we consider is a little bit different. Yeah, what is the difference? Let's pay attention to the difference. Instead of ut, we have wt minus 1, and here the time is reversed. So if we look, let's say that this is equation number 1, and if we look at our new equation number 2, so let's recall equation number 1. It was yt is equal to 0.5 ut minus 1 plus ut. Okay, if we pay attention to the difference, basically we have renamed the white noise. Okay, we have renamed the white noise, and we have t minus 1 and t here, and t minus 1, the time is reversed. So hence, I can easily find the solution, okay? Whatever the solution. Yt minus 1 will be equal to Wt minus 1 plus 0.5 Wt plus 0.5 square root Wt plus 1 plus 0.5 cube Wt plus 2, and so on. So you may easily check that this is the solution of equation 2. Let's check that everything is okay. Yeah, let's check that that it's really a solution. Yeah, well, let's check this. Plug these into the left-hand side, plug these into the right-hand side, and let's check that everything will cancel out. Let's check Wt minus 1 plus W5 Wt plus 0.5 squared Wt plus 1 plus 0.5 cube Wt plus 2 plus dots. Is it equal to 0.5 times Wt plus 0.5 Wt plus 1 plus 0.5 squared Wt plus 2 plus dots plus Wt minus 1. And we see that everything cancels. Everything cancel out. Okay, that cancel out. That. And so on. Yeah. And this is really a solution to this equation. So let's rewrite it. Let's go back from W to U. So let's go back to our original variable, because we have written this equation in terms of W. Okay. So let's write Yt minus 1 is, what is this? It's minus 0.5 Ut minus 0.5 square root Ut plus 1 minus 0.5 cube Ut plus 2. Or if I'd like to find Yt, that will be minus 0.5 Ut plus 1 minus 0.5 Ut plus 2 minus 0.5 cube Ut plus 3, and so on. And so this is the solution, one of infinitely many. Yeah, we remember that every equation, every recurrent equation has infinitely many solutions. Yeah, remember that's true for this equation too. I can use any y0, and using any y0, I will obtain a valid solution for all y's, y1, y2, y3. Hence, we have obtained that that's a solution of equation 2. And by the way, we know that this solution is stationary. Yeah, it has the same structure for y1, the same structure for y2, the same structure for yt, y5. So this is stationary solution. Stationary solution. You may check expected value of yt will be 0. Variance of yt will be minus 0.5 square root sigma square root u plus minus 0.5 square root sigma square root u plus bam. That's constant. So that's a stationary solution. But is this solution, is it MA infinity process with respect to yt, to ut? And the answer is no. It is stationary. Yes. Is it MA infinity? Let's recap. What is MA infinity? Who remembers what is MA infinity? Yeah, let's recall what is MA infinity. MA1 is a process of the form ut plus ut minus 1. MA2 is a process of the form ut plus some coefficient before ut minus 1 plus some coefficient before ut minus 2. If we say MA infinity, then yt should be equal to ut plus some coefficient before ut minus 1 plus some coefficient before ut minus 2 plus some coefficient before ut minus 3, and so on. And this solution does not have this form. Yeah, that's not an MA infinity process, because in my solution, coefficients, indices, they go into the future. And for moving average process, indices should go into the past. Yeah, that's very strange solution that some authors of economics books and not only economics, in many physics application, it would be strange that current value of the process depends on the future shocks. So from mathematical viewpoint, that's a valid solution of equation, but some authors say that, oh, we do not like to work with this solution because it makes no sense from interpretation viewpoint. If we'd like to interpret ut as something that happens as something random that happens at time t. So some authors, some books, they exclude these solutions looking into the future. From mathematical viewpoint, this is absolutely valid solution of the equation. It's valid, it's stationary, it's a honest solution. Even more, it's a stationary, honest solution. But the expression for yt depends on future values of noise. And if you'd like to interpret like ut is something that happens at time moment t, ut plus 2, that's something random that happens at time moment t plus 2. And you say, oh, that would be strange, that's something real, some, I don't know, the temperature today includes the shock to the temperature that will happen tomorrow and after tomorrow. That's a little bit strange. From interpretation viewpoint, if I'd like to interpret ut plus 1 as something that happens at the moment t plus 1. So that's the difference between the second and the third definition. Yeah. According to the second definition, the solution we have discussed is autoregressive process of order 1, because it's a solution, it's stationary. But from the third viewpoint, the solution we have discussed is not an autoregressive process, because this solution uses future values of u. MA infinity means basically that yt includes only ut minus 1, ut minus 2, ut minus 3, and so on. And MA infinity form, that means there are no ut plus 1 in yt, there are no ut plus 2 in yt. And in the solution we have provided, we see that there are future terms in yt. And hence, that's a honest solution from mathematical viewpoint. It's stationary solution, but it's not of moving average infinity form. Okay, that's clear. So that there are three approaches to define what is the autoregressive process.
Okay, I think I just a bit forgot what does mean MA.
MA?
Yeah.
The definition, we are happy that the definition of MA infinity is unique. Okay, so every student should be happy at this moment of time. MA infinity in all books, it means YT is some constant plus UT plus let's say beta 1 times UT minus 1 plus beta 2 UT minus 2 plus beta 3 UT minus 3 plus UT is a white noise.
And so RR will be without C, right?
Sorry?
And AR will be without C, right?
No, the question is no. No. AR means there are YT in both sides of the equation.
I see then. And no, this is the degree?
Sorry. I'm talking that there are three ways, three groups of books, three groups of authors. One book, they say that any solution of this equation is autoregressive process of order 1.
Sorry. I see then. Yeah. I just, yeah. Then I got what we're talking about. It's just, I was confused with the seminars, so I see then. Yeah.
Okay. So let's let's calculate some properties using so let's probably calculate some properties using different assumptions. Okay, so let's calculate exercise. Let's say YT is 2 plus 0.7 YT minus 1 plus UT. UT is a white noise. White noise. Okay, my question A. Can we find the expected value of YT or variance of YT without additional assumptions? So that's the first question. Can we calculate expected value of YT or variance of YT without additional assumptions? So if I just give you the equation and I give you that UT process is a white noise, can we find expected value and variance? Oh, the answer is no. No. Because we can, as we have discussed, we can pick any value of Y0. So if you say Y0 is 25, then expected value of Y0 will be 25, and expected value of Y1 will be 2 plus 0.7 expected value of Y0 plus expected value of U1. It will be 2 plus 0.7 times 25. And if, for example, you say, oh, no, this is an equation, but I'm free to specify Y0. Let's say Y0 is 100 plus U0. And in this case, expected value of y0 is 100 plus expected value of u0. U is white noise, so hence it's 100. And expected value of y1 is twice 2 plus 0.7 times 100 plus expected value of u1. It will be 72. And you see well that if you just write the equation and you write that yt is a white noise process, you have too many degrees of freedom. You can't find the expected value. Yeah, expected value can be 25, can be 100, can be 1000, can be, I don't know, -4. So we are free to choose y0. That's the first point. Sorry, the second point of my discussion, that this equation has infinitely many solutions. Now, point B. If I say additionally that let's consider not every solution, but a stationary solution. So let's consider a stationary solution. Stationary solution of this equation. Can we calculate expected value of yt? Can we calculate correlation of, I don't know, yt minus 1? So that will be equation star, or maybe equation, oh, let's say equation sum, because I think I have already introduced equation star, so it will be equation sum. And the answer changes. If I additionally assume the stationarity, then that's not a problem to calculate characteristics of this process yt. And so in many cases, so when you use Python stats models or skTime to analyze time series in Python, when you say, oh, I'd like to estimate AR model, and Python implicitly assumes stationarity. And that's why that's important to understand which assumptions are used. So without additional assumptions, this equation leaves you too many freedom. You can't calculate even expected value. But with the assumption of stationarity, let's look how the situation changes. So let's calculate expected value of yt. That's expected value of 2 plus 0.7 times yt minus 1 plus ut. So that's 2 plus 0.7 times expected value of yt minus 1 plus expected value of ut. And that is 0 because ut is a white noise. And we have an equation that expected value of yt is 2 plus 0.7 times expected value of yt minus 1. But as we consider stationary solution, as we consider stationary solution yt, then for stationary solution, these expected values should be equal for stationary solution. These are equal for stationary solution. If they are equal for stationary solution, let's say they are mu y twice plus 0.7 times mu y. Hence, we've got 0.3 times mu y is 2. Mu y, expected value of yt, is 220 divided by 3. And we have calculated expected value of yt. But to calculate it, we need to make an assumption that we are searching for stationary solution. If you don't make this assumption, you need to specify y0. If you consider any solution, then to calculate expected value, you need to specify y0 or I don't know, y5, y10. So you need to specify something additionally to calculate expected value. The equation sun itself is not sufficient to calculate expected value. So you need to make some assumptions, some more assumptions. Either you specify some particular value of y, either you specify that, oh, I'm working with a stationary solution of this equation. Because equation sun, as we have discussed, the equation sun has infinitely many solutions. Okay, now let's calculate correlation. So correlation is also possible to calculate under additional assumption of stationarity. How we can calculate it? Let's recall the definition of stationarity. For stationary process, variance of yt is equal to variance of yt minus 1. We need a theorem from lecture to continue, I hope, or no? Yeah, we need a, okay, so let's, variance of yt minus 2. I need a theorem to continue to calculate correlation. I need a theorem. I think we will not prove it. No, we will not prove it. That's a little bit hard. We need a complex analysis and some deep understanding of complex analysis to prove, but we will state the theorem. Theorem. Equation of the form yt equals to some polynomial, let's say a of L times yt minus times yt plus ut, where a of L is some polynomial with degree of a big or equal to 1, and ut is a white noise. This equation has at most one stationary solution. Equation of this form has 1 or 0 stationary solutions. We will not prove this theorem. This theorem is the main reason why many authors, they implicitly, sometimes explicitly, but in many cases, they are either too professional and they do not specify all the details because they are professional and they know very well what they are speaking about. And some authors are not so professional and they just forget to specify this subtle detail that, okay, let's consider only stationary solution of this equation. Yeah. So be careful. And in modern time, when on the internet many authors copy parts of the text of other authors, and you have ChatGPT, then in modern times that will be a problem to obtain a correct theorem for autoregressive process. Okay, so this theorem says that if we add the stationarity assumption, so if we work with point B, if we consider the stationary solution, then this stationary solution is either non-existent, either unique. So there will be no different answers between authors. So if I say, oh, let's consider this equation and the stationary solution of this equation, then you can't obtain expected value equal to 20/3, and I will obtain expected value equal to, let's say, 5, because we are working with different stationary solutions of this equation. Yeah, we have a theorem that says that if we restrict attention to stationary solutions, then there is only one or even zero stationary solutions, and hence all characteristics we will calculate if we assume stationarity, they will coincide. So if I do not assume stationarity, then I can calculate, then I have many solutions, and then I can obtain any expected value I wish. But if I assume stationarity and some other guy, some other researcher assumes stationarity, then we will both get the same expected value. We will both get the same correlations. Then we will get the same variance, because we have a theorem that guarantees that stationary solution is unique. Okay, using this theorem, let's explicitly write the solution. Okay, okay, we have an equation. I forgot the equation. Oh, that's our equation sun. Yt is equal to 2 plus 0.7 times yt minus 1 plus ut. Okay. The trick, you already know it. So you just plug in, because of the theorem that guarantees that there are no other stationary solution, and then you can just guess one stationary solution, and that's fine. You can study its properties. So this theorem is very useful. Okay, so let's plug in yt in place of yt minus 1. So we will get 2 plus 0.7 times 2 plus 0.7 times yt minus 2 plus ut minus 1 plus ut, or we will get 2 plus 0.7 times 2 plus ut plus 0.7 times ut minus 1 plus 0.7 squared yt minus 2. We can repeat this process and plug in yt instead of yt minus 2. If we do this, we will obtain 2 plus 0.7 times 2 plus 0.7 squared times 2 plus ut plus 0.7 times ut minus 1 plus 0.7 squared times ut minus 2 plus 0.7 times yt 0.7 cubed times yt minus 3. And you can guess that if we continue this process infinitely many times, then this term will go to 0 if we assume stationarity. That's an important point. If we assume stationarity, then we multiply something that tends to 0 by a random variable with constant expected value, constant variance. If we multiply a random variable with constant expected value and constant variance by something that tends to 0, we'll obtain some random term that tends to 0. And hence, under stationarity assumption, we can do this infinitely many times. And hence we obtain the particular solution. Yt is twice plus 0.7 times 2 plus 0.7 squared times 2 plus blah, 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 L dots. ut plus 0.7 times ut minus 1 plus 0.7 times square root times ut minus 2 plus 0.7 cubes times ut minus 3. And we have a solution, this solution, that is solution to equation sun. And that solution is stationary, and it's of MA infinity form, because yt includes ut, ut minus 1, ut minus 2, ut minus 3. There are no terms from the future. Yeah, yt includes only past terms. Okay, so we see that that is solution, that is stationary, that has a MA infinity form. A MA infinity form, in particular, we can conclude that covariance of this particular solution, yeah, I calculate the covariance of this particular solution, yt and ut plus 1, that is 0. Why it's 0? Because there are no ut plus 1 in yt in this solution, yeah, in this solution. If you consider some other solution, yt may include ut plus 1. Okay, we can even more conclude that covariance of yt and ut plus 2 is 0, and so on. Yeah, but my goal was to calculate correlations. Yeah, finally, let's, under all these details, let's finish the answer to our question, and let's calculate correlation of yt and yt minus 1. Once again, I go back to my equation sun. I have an equation sun. Yt is equal to 2 plus 0.7 times yt minus 1 plus ut. Once again, I'm searching for the stationary solution. So we consider stationary solution. We have proven that it has a MA infinity form. We have proven that it has a MA infinity form with respect to ut. And hence, that's enough to calculate correlations. Let's calculate covariance. Let's calculate covariance of yt minus 1. Covariance of yt minus 1, I can plug in yt. So that's covariance of 2 plus 0.7 ut minus 1 plus yt minus 1 plus ut with yt minus 1. 2 does not influence covariance, so it will be 0.7 covariance of yt minus 1 plus covariance of ut yt minus 1. That is the variance of yt minus 1, and that is 0 because yt has a MA infinity form. And hence ut minus 1 includes only yt minus 1 includes only ut minus 1, ut minus 2, ut minus 3, and so on. Hence, we have proven that covariance of yt minus 1 is 0.7 times variance of yt minus 1. Okay, let's calculate correlation of yt minus 1. That's covariance of yt minus 1 divided by square root of variance of yt variance yt minus 1. We once again, that's important to point out that we consider stationary solution. Yeah, in the point B, once again, we are solving not the point A, but we are solving the point B, where we assume stationarity. And if we assume stationarity, then under stationarity, then variances are equal. We have variance yt, so it's covariance of yt minus 1 divided by variance, and we see that covariance divided by variance is 0.7. I hope that's all for today. Let's summarize a little bit the problem. When we talk about moving average of order 1, moving average of order infinity, moving average of order 2, that's not a problem. All definitions in all the books, they do coincide. So that's a standard. The problem arises when you speak about autoregression, and there are 3 traditions. So, for example, if you will use stats models or SKTime in Python, and you will say, oh, I would like to estimate AR1 process, it will use the third definition. That's built in software. Yeah, the authors of the designers of software, they have decided that, okay, when you ask Python, SKTime, or stats models to estimate autoregression of order 1, they will use a third definition that they assume stationarity, they assume a MA form with respect to the noise in the equation. If you read some other books, and in some other books you may encounter, oh, this solution is autoregressive process of order 1, and it's even not stationary because the author uses the first definition. So be careful. And if you ask help from ChatGPT, be careful, because it may freely mix different sources from the web, and hence be careful. Some statements will be false. If you mix the theorem in the third style with the definition of the first style, obviously you will get a wrong statement. So that's the only point. And then we have calculated some characteristics. And my point is that this equation has infinitely many solutions. So without additional assumptions, you can't calculate even expected value. You're free to obtain any expected value. But if you add the requirement of stationarity, then you have a theorem that we will not prove, we will believe in this theorem, that you will get almost, or at most, one stationary solution, and hence you can study, you can calculate expected value, correlations, covariances, I don't know, variances. That's all for today. I hope we have discussed the main pedagogical problem with autoregressive process, that there are 3 types of definitions. Okay, thank you very much. Check.
Thank you, goodbye. Thank you for the lecture.
Because next time we will be offline and online simultaneously, so if you'd like to be present offline, so check the schedule. Bye-bye.
Bye-bye.